So we got through 4.3 right before the break, and so we're going to start with 4.4 now. And I want to kind of just pause and see if you remember something kind of important, and that is, if you look at the title of the notes, it's called Observational Studies and Experiments. And right before the break, we, actually in 4.1, at the beginning of the chapter, we talked about the difference between those two. So let's look at this little review question and see if we read through this, if we can figure out if this is describing an observational study or an experiment, because that's question A. It says, does eating dinner with their families improve students' academic performance? According to an ABC News article, teenagers who eat with their families at least 5 times a week are more likely to get better grades in school. This finding was based on a sample survey conducted by researchers at Columbia University. So if I'm reading through this, it's really important, if I already know the question is asking me to distinguish between observational study and an experiment. If you remember way back to the beginning of the chapter, an experiment is where you impose some kind of treatment. So you would like split your people up into 2 groups and impose some sort of treatment to kind of compare them. And that's really not what they're doing here. All they're doing is they took a sample survey, and for me, that's the giveaway. They just asked people, hey, maybe they asked, how many times do you eat dinner with your family? Or maybe it was just a yes or no. Do you eat with your family at least 5 times a week? And what are your grades in school? It's just a survey. Therefore, it's an observational study. This isn't even an experiment. So that allows us to answer part A. This was an observational study. And it says to justify your answer, and I'm just going to do that by saying, well, the phrase sample survey gave it away for me. I don't need to write a big fancy sentence about why. Those 2 words let me know that this was just an observation. They didn't impose a treatment on any groups of subjects. Part B is also a review question. We've got this vocabulary here, explanatory and response variable. Those are the variables. Those are things that are going to change from person to person. So I may ask how many times you eat with your family a week. That's going to vary from person to person. So that's a variable. And what are your grades in school? That's going to vary from person to person. And so one of those will help explain the other one, and that would be the explanatory variable, and then the other one is the response variable. So out of these 2, if we're thinking that teenagers who eat with their families at least 5 times a week get better grades in school, which one explains the other? The number of times a person eats with their family or the grades in school? The number of times you eat with your family would help explain what your grade in school is, according to this study. Now, we may debunk this here in just a second, but if we just kind of keep going with the flow, the explanatory variable is going to be the number of times a person eats with their family per week. Number of times a person eats with family per week. I know that's a variable, once again, because it's going to vary from person to person. The other variable, basically the other thing that's going to be a different answer from person to person, is the grades that you make in school. So that's going to be the response variable, grades in school. But here's the problem with this. Sometimes we read these things in headlines and we just take them at face value. Wow, maybe if I eat with my family 5 times a week, my grades will improve as well. So part C says, explain why such a study cannot establish a cause and effect relationship. In other words, are there other variables that could cause students who eat with their families to have better grades? So you're probably already thinking, this has nothing to do. I'm an A student, and I don't eat dinner with my family 5 times a week. I have a job and all of that kind of stuff. So what are some other factors that maybe we could think of? These students who get to eat dinner with their families a lot, are there other things about their lives that could contribute to them having better grades? What do you think? What might be true if you have the time to eat with your family 5 times a week? What might that mean about your outside of school time? You probably don't have a job that you're trying to manage, right? You're probably not involved in a ton of extracurricular activities. You just basically, you have more free time. If you have enough time to eat with your family that frequently, you've probably got less on your plate, no pun intended, than somebody who is busy all the time. So that may contribute to you having better grades. Okay, this is leading us up into a really big, important concept called confounding. So let's just jot down some ideas right here. Students who eat with their families are more likely to have more spare time to do their homework. These students are likely, not necessarily, but they're likely to have more spare time These students are likely to have more spare time to do homework. That might contribute to better grades. They are less likely to have jobs. Let's just put they're less likely to be busy with other things. Now again, we use words like likely and unlikely because it's not a for sure thing. Some of you may have a job and you still get to eat dinner with your family 5 times a week. Okay, so we're just talking about some things that could contribute and not necessarily make this connection between eating with your family a specific number of times a week and your grade in school. What we just did there is we came up with some other variables that could contribute and kind of confuse this cause and effect relationship, and that's called confounding. And this exact definition is going to show up on your next test. Confounding. It's a big concept in statistics when you're designing a study or you're kind of analyzing the results of a study or an experiment that you do. Confounding occurs when two variables are associated in such a way that their effects on a response variable cannot be distinguished from each other. In other words, in this particular example that we're talking about, eating with your family and your grades, the response variable is your grade in school. There's more than one explanatory variable that would contribute to that, and we're not really sure which one contributes to that. So we can't distinguish those from each other, and that's called confounding. It's important for you to know that statisticians take very careful steps to prevent confounding. A well-designed experiment or observational study will prevent confounding. So you may see a homework problem like this, example number 1, and I want to make sure you feel comfortable with it. It says, in a study of more than 4,700 children, researchers from Cincinnati Children's Hospital Medical Center found that children whose mothers smoked during pregnancy were more than twice as likely to develop ADHD as children whose mothers had not smoked. So that seems like it would be pretty clear cut, right? But it says, based on this study, is it reasonable to conclude that a mother's smoking during pregnancy causes an increase in the risk of ADHD in her children? So is there a direct cause and effect relationship there, or could there be other factors that would contribute to a mother smoking and her children having ADHD? So again, we're trying to see about this cause and effect relationship. Now, you have to kind of keep an open mind here and know that we're not saying that every single person who smokes is a garbage person or anything like that. But if you smoke, more than likely you're probably not somebody who has a stellar diet, somebody who goes to the gym regularly and takes really, really good care of your health. Those things typically don't go hand in hand. So what we're going to say here is that there's really not proof that smoking is what causes the ADHD, because a person that smokes while pregnant might be less likely to have a good diet or exercise, and so that could also be a contributing factor to the ADHD, not just the smoking, okay? So I want you to start by writing no. We're answering the question, can we conclude that smoking causes ADHD directly? And really we can't. The reason is, it is possible that women who smoke while pregnant have less healthy diets, and don't exercise regularly. And you may even be able to think of other variables, other unhealthy habits that a person who smokes while pregnant might have. But we'll just kind of stick to diet and exercise. So perhaps these variables contribute to an increase in ADHD. Perhaps these variables contribute to an increase in ADHD, not just the smoking. Now, is there a relationship there? Probably, but we can't say that it's all chalked up to just the smoking. It's called confounding, when two or more variables are associated in kind of a confusing way. I always think of confounding as confusing. Okay, I think the rest of the notes are actually a lot easier than that whole concept of confounding, okay? So here's some vocabulary words I think you'll pick up on pretty quickly. Recall that an experiment deliberately imposes some treatment to individuals to measure their responses. Each of these individuals is called an experimental unit or subject. So right here we've got 3 vocab words you'll see on your next quiz. If I say we've imposed some kind of treatment, then that's just a specific condition that I've applied to the individuals in an experiment. At the beginning of this class, we talked about how individuals don't necessarily have to be people. They can be trees, they can be animals. So individuals don't have to be human. Individuals are called experimental units. Those are the objects to which a treatment is randomly assigned. We call those experimental units. Most of the time in statistics, you're talking about people. If your experimental unit is a person, we call that a subject. A subject is when the experimental units are human beings. So it's just a little bit more specific. If you read the word subject, you know that this study or this experiment is being done on human beings versus rats in a lab or something like that. This next example is the mathy part of the day. Don't let that scare you. It's extremely easy. Let's read this and see what it wants from us. Researchers invited 186 university students to take part in an experiment. It says it's an experiment, so we should be able to see 2 treatments imposed. While the students were watching a video, they were given cookies to snack on. Unknown to the students, the size and number of cookies differed from student to student. There were 3 different sizes of cookies, 8 grams, 16 grams, or 32 grams. And there were 4 different quantities of cookies. Some students got 1 cookie, some got 2, some got 4, some got 8. And then researchers, so those are the treatments that were imposed, and researchers measured the total weight of cookies consumed and whether each student finished the cookie. Okay, doesn't really say like what they're trying to figure out by doing this. It's just saying, hey, we gave people different sizes of cookies, different amounts of cookies, and we recorded how many they ate. That's all, while watching TV, watching a video. So part A says list the explanatory variables, there could be more than one, and the number of possible values from each variable. So don't overthink that. The variables here, the things that vary from subject to subject, are the sizes of the cookie. It says, you know, give all the values. Well, all the options for sizes of cookies were 8 grams, 16 grams, or 32 grams. That was one of the explanatory variables. And there's another variable, and that's the quantity or number of cookies. You could have 1, 2, 4, or 8 cookies. There's more than one variable here. And when it says to give the number of possible values of each variable, I'm just listing them out here. There are 3 different possible values for number of cookies, or excuse me, size of cookies, and 4 different possibilities for quantity. That's going to be important to answer part B. Part B says if the researcher uses every possible combination to form the treatments, how many treatments were included in the experiment? So this is the mathy part. Watch how easy this is. Well, there are 3 sizes, and you would just multiply that by 4 quantities. That means there are 12 different treatments that could be imposed. 12 treatments. That's as mathy as it gets today, multiplying 2 integers together. Easy peasy. And you will have a homework problem like that. You'll get a much bigger answer on your homework problem because there will be a lot more variety of treatments and variables. But that's it on part B. Now, part C just says list at least 3 of the treatments. You don't have to get carried away. Let's list 3 treatments. I'm going to throw this out there. I could have given somebody 2 16-gram cookies. That's one of the possible treatments. Give me another one. What could I have given?
8 grams.
8 what?
8 grams.
Okay, 8-gram cookies could have been given to somebody. Give me one more. Don't overthink it. What about 1 32-gram cookie? And there are 12 different ones you could list, okay? There are 12 different treatments. Part C just wants you to list 3 of them so that you're understanding, you're proving that you understand what those 12 different options are. So just list 3 and you're done. On your homework, if it says to list 2, list 4, whatever it says. Okay, let's look at this next part, experiments comparison. A student wants to investigate whether caffeine affects pulse rates. The student proposes the following plan. Have each student in the class record their pulse rate. So like right now, if I said stop, you're going to record your pulse rate. And then I'm going to give you all, everybody in here, 12 ounces of soda. Wait 15 minutes. And then take your pulse again and compare your pulse rate. Doesn't really seem like too bad of a plan. This seems like a great plan until we consider confounding variables. There's that word again. Variables that could confuse the process. What else could cause pulse rates to increase instead of just the caffeine in the soda? What do you think? Stress? Like, yeah, what if we had some kind of like lockdown drill in the middle, or you didn't know if it was a drill or not, and you were stressed out, and you're like, oh my gosh. So let's say stress caused by the environment. What else in soda could maybe cause your pulse rate to increase? Sugar could be in there. Yeah, it doesn't say that they use sugar-free or anything, so that could be a confounding variable. Sugar in the soda. I mean, we could keep on listing. There are other things that can make your pulse rate go up. Even though you just had soda, we can't say it's necessarily the caffeine from the soda that made your pulse rate increase. That's called confounding, so I hope that concept is getting a little easier for you. The solution is to have two groups in the experiment. One group that receives caffeine and a control group that doesn't receive the caffeine. Okay, control. They're not going to get the caffeine. On your next test, you're going to need to know what a control is, control or control group, and why that's helpful or beneficial in an experiment. Why is it necessary to have that? Most of the time you want to have a control group. On the next page I'll give you an example of you don't always have to have a control group. But it's a pretty good idea in an experiment like this because it will give you a baseline. Control groups are used to provide a baseline for comparing the effects of other treatments. So if everybody gets the same thing, but some of you get the caffeine and some of you don't, then maybe I can be a little bit closer to finding that cause and effect relationship. Maybe it was the caffeine that increased the pulse rate. So depending on the purpose of the experiment, a control group may be given an inactive treatment, an active treatment, or no treatment at all. So let's answer this question at the bottom of the page before we get to the last page of the notes. It says, what are some possible ways the student could design a better experiment to see if caffeine affects pulse rate? So let's say we want to take these variables out of it, like the sugar. So what's one way I could tweak this where we could take sugar out of the confounding part? You could use a sugar-free drink. That way we know that sugar is not contributing to pulse rate. Or you could have two groups, and one of them could get soda with caffeine, and the other could get the same exact soda without caffeine, so like caffeine-free. So let's write one group gets soda with caffeine. Other group, one group gets soda with caffeine, other group gets caffeine-free. And that's probably the best way. If you're designing an experiment, those would be your two treatments. If you'll turn the page, there's a little caution symbol, and it's just there to say, you know, you don't always have to have a control group when you're designing like a well-designed experiment. And the example right here is, let's go back to that cookie thing, okay? I'm giving everybody different amounts and different sizes of cookies. There's really no, and seeing how much they eat, there's no reason to have a control group. Like, there's no reason to have, look what it says, having a control group who received no cookies really wouldn't be beneficial, because guess how many cookies they would eat if they didn't have any in front of them? 0. So it's just, it doesn't really make sense. It's not necessary in an experiment like that, okay? In the caffeine-free experiment, we used comparison to help prevent confounding. But even when there's comparison, confounding is still possible. I want you to highlight that. Even when there is comparison, confounding is still possible. It almost seems like we can't get rid of this confounding business. But we can, if we're even more careful. If each student knows whether they're receiving caffeine or not, the expectations will be different. If you're a student that knows I'm about to drink caffeine and this experiment is about increased pulse rate, that can actually, in your mind, increase your pulse rate. If you know you're receiving the caffeine-free stuff, then there's a chance that in your mind that causes your pulse rate to just stay the same. It's called the placebo effect. Okay? So here's what that is. By definition, and this could show up on your next quiz, placebo effect describes the fact that some subjects in an experiment will respond to any treatment, even an inactive one. That inactive one is called the placebo. So the placebo effect is basically your mind interfering with the results. So it's best if you really don't know what kind of soda you receive at all. To make sure the expectations of all students in the class are the same, we could give one group soda with caffeine and the other group a placebo, a soda that is basically identical but without the caffeine. So a placebo, by definition, is a treatment It's a treatment that has no active ingredient. But otherwise is the exact same as all of them. You don't want to have like two different colors of soda and then be like noticeably different, you know, using your eyes you can tell. So it's got to be the same in all the other ways except the placebo would have no active ingredient. Now typically when you're reading a statistics problem, that's going to be like a sugar pill. You'll see lots of trials for like testing whether a drug reduces your chance of having a heart attack or something like that. So you would get a sugar pill, it's called a placebo. But it can be any other type of substance that looks, tastes, smells, and feels the same as the other treatments. That's what a placebo is. Okay, our last two vocabulary words here, these will show up on your next test. So let's kind of wrap this up. There's not going to be a whole lot for you to write, so just listen. Of course, a placebo is only useful if a subject doesn't know they're receiving it. If you know you're taking a sugar pill in an experiment to see if aspirin reduces heart attack, and you know you're not taking the aspirin, then that's not going to be useful. If none of the students receiving soda know who's getting what type, this is called single-blind experiment. If none of the students nor the people running the experiment, let's say the teacher, if nobody knows who's getting what treatment, it's called double-blind, and that's really the best way to do it. So let's define these here. Single-blind is when either the subject or don't know really what's going on. They don't know who's getting the placebo. They don't know who's getting what treatment. So either the subjects or the person in charge. But a double blind is even better because neither, neither the subjects nor the people conducting the experiment know what treatment is being received. So double blind is really the best. But just know that this is probably the best. Those will kind of show up on your, we just barely touched on it in the notes, but it's an important concept and it'll show up on your test, okay? And that's pretty much it. If you're interested in reading on a little bit more about why placebos work, I've got that little box there for you.